Hello everyone, welcome to Driving Approach. My name is Alexei and you are watching Mechanics Corner. Today we're going to talk about the displacement of the engine and the compression ratio of the engine. And in order to understand both of these things, we would need to look at some other things other than what we looked at before. One of those is the bore of the cylinder, which is pretty much the distance between the left side all the way to the right side of the cylinder. So it's the diameter of the cylinder, and the stroke, which is the distance that the piston travels from top dead center to bottom dead center, or from bottom dead center to top dead center. And both of these are measured in units. For example, usually they're measured in millimeters, just like you can see here. So bore, as we figured out, is from here to here, stroke is from here to here, and the next thing that we need to look at is the swept volume. And the swept volume is pretty much the engine displacement, or the engine size. It's the space available for the engine to take in the air-fuel mixture, or if it's a direct injected engine or diesel, space available to take air in. And in order to calculate that, we would need the bore, we would need the height, which is the stroke, bore, which is the diameter, or diameter divided by 2 is the radius, the stroke, which is the height, and the P or pi number, which is 3.14 pretty much. We're going to use it as an example, a Hyundai Elantra engine, which is a 2-liter engine. Measurement for that engine is bore is 81 millimeters and stroke is 97. So bore, we're going to divide by 2 because we need the radius, which would be half of the bore, and the bore for that Elantra engine, the 2-liter engine, is 81 millimeters, and the stroke is 97. And it's important to remember the units that you're using. We're in millimeters. So if you take and multiply this by that squared and multiply by that, we'll get 499,587.35 millimeters cubed, because it's volume. Another thing that we need to understand is that 1 liter equals 1000 cc's. Cc's is cubic centimeters. We have cubic meters here, and cubic millimeters here, and cubic centimeters there. And if we express this number in cubic centimeters, it would be just 499, or we'll just round it up to 500 centimeters cubed, which then would equal to 0.5 meters cubed, which then leads us to 0.5 liters. And that's the swept volume, or the displacement, for this particular cylinder of that 2-liter Elantra engine. And to get the displacement of the whole engine, we just need to multiply this by 4, because that car has 4 cylinders, which will give us the 2 liters. Okay, so we'll do the same calculation, but for another car, which is the Genesis G70 3.3 liter. So we'll just erase this. And it has a slightly different bore and stroke. It will be still millimeters. So it has a 92 millimeter bore, and it has a 83.8 millimeter height or stroke. And if you calculate this, it will give us 5, 5, 6, 787.31 millimeters,
which in
cubed, which in centimeters will give us obviously 556. Well, we'll round it up to 7 because we carry from the 7, so 557 centimeters cubed, which will then give us a 0.557 meters cubed that give us 0.557 liters. 0.557 liters, and that's the displacement or the swept volume for one of the cylinders of the Genesis G70 3.3 liter engine. And because that's a V6 engine, we would multiply this by 6, which will give us the 3.3 liter, which is the displacement that that car has. Okay, so we've talked about the displacement, which is pretty much the space that the engine has available to take in the air-fuel mixture to then be able to compress it and ignite it. And the next thing that we're going to talk about, which is the compression ratio, actually comes out of the swept volume, because the compression ratio is the ratio of the compression chamber, which is anything that's left in the cylinder when the piston is at the top dead center. And obviously, because piston would be here, anything that's left would be up higher than the piston. And the compression ratio is how many times this compression area fits into the swept volume. So, for example, for the Elantra, because you can search up the compression ratio for different engines and different cars. For the Elantra, the compression ratio, so we're going to write it out. So we're talking about compression ratio, which equals to swept volume that we just calculated, divided by
the
compression chamber volume. This one, compression chamber volume divided by compression chamber volume. Obviously, in order to calculate the compression ratio, you would need to know the compression chamber volume, but it's not usually available or given. But the compression ratio is. And since we have calculated the swept volume or the displacement of the engine or the individual cylinder, and we were able to search up or find the compression ratio for a particular engine, we can actually calculate the compression chamber volume, which we will do. So then, because the swept volume is the largest number in this equation, because it's being divided by this, that gives us the answer, we can just flip these two, and this way we'll be able to find out the compression chamber volume. So to find the compression chamber volume, we just need to divide the SV, swept volume, or the engine displacement, by the compression ratio. And as we calculated the swept volume for the Elantra was, for one of the cylinders on the Elantra was 500 centimeters cubed. If we divide that by the compression ratio of the Elantra, which is 12.5, we'll calculate that the compression chamber volume is 40 centimeters cubed. And as you can see, this can fit into here 12.5 times. Same as this can fit into here 12.5 times. So you'll be able to actually literally fit this 12 times, and then there will be enough space for just half of this volume. And this is the compression ratio of the engine, well, or each individual cylinder. And we can do the same calculation for the Genesis, which will give us very similar compression chamber volume and a compression ratio for the Genesis is 10 to 1. This one is 12.5 to 1 because one compression chamber volume can fit 10 times into the swept volume for the Genesis, or 12.5 times for the Elantra. So if we want to calculate the compression chamber volume for Genesis, we'll be dividing the swept volume by the compression ratio, which is 10, and the swept volume is 557 centimeters cubed. This will give us a 55.7, my bad, 55 centimeters cubed as the compression chamber volume. So this is going to go into here 10 times. And that's pretty much the displacement of the engine and the compression ratio of the engine. Another word for combustion chamber volume is actually the clearance volume, because the piston is at the top dead center, both valves are closed, and that's the clearance, that's kind of the clearance that's left, because that's the only space between the piston and the valves that's left in the cylinder. And as you can see, the swept volume is the volume from top dead center to bottom dead center. So technically it doesn't include the clearance volume or the combustion chamber volume, how I call it. But that's how we refer to engine size, which we call it the engine displacement. So because it's the movement of the piston that takes stuff in and pushes it out. So that's why we calculate the swept volume, and it is the engine displacement, and we also call it the engine size. And that's why they write the 2.0 liter car, just like we calculated for the Elantra, the 3.3 liter, or the 6.3, like some of the AMG Mercedes cars have. And that would be the engine displacement, meaning it's the volume of all the cylinders in the engine together, but each cylinder is calculated using the stroke and bore, just like we did here. I'll talk more about the displacement and how it affects the characteristic of the engine, and the compression ratio and how that affects the characteristics of the engine outside. Yeah, so I'll see you outside and we'll continue there. So we're outside now. We have a different car,
And
in this video we started talking about the engine displacement or engine size, and we also talked about the compression ratio of the engine. The car that I had in the previous videos, the Elantra, the blue one, was a 2-liter car, and that was the displacement or the engine size in that car. In this car it's a 3.3 liter, that's the engine size, and we actually calculated the we took the bore and the stroke for this engine and for the 2-liter from the Elantra, and we calculated the engine displacement indoors, and we also looked at the compression ratio and how it's being calculated. I just want to go to the back of this car just to show the 3.3, just to show the 3.3 symbol, because it is related to what we're talking about right here. Before the turbos became so mainstream on street cars, the engine displacement was a really good indication of how powerful the car or the engine is. So if you would be comparing like a 1.8 liter engine to like a 3-liter engine, the 3-liter engine would probably be more powerful. But it's hard to use that as a reference right now, because most of the cars on the streets and newer cars are turbocharged. So, and with the turbocharged, you can introduce so much air to the combustion chamber, plus introducing enough fuel, and it will be producing way more power. So the engine displacement right now is not a strong determinants of which car would have more power. If you're just comparing the displacement, you would need to look at many other things. But still, you know, if a car is like a 2-liter and a 5-liter, and then if they both would have, if they're both like supercharged, the 5-liter engine would probably be more powerful. As you have noticed from the calculations that we did indoors, that the compression ratio of the Elantra, of the 2-liter engine, is higher. It's 12.5 to 1, and the compression ratio of the 3.3-liter Genesis engine is actually 10 to 1. Some of the reasons why it's like that is because the 2-liter Elantra engine is not turbocharged. So to get that extra power that will be needed, they needed to design the engine so it would have a higher compression ratio. With the higher compression ratio, you obviously can have a higher chance of knock or detonation. The reason is because you're just trying to compress harder or more if you have a higher compression ratio. In terms of choosing between a higher compression ratio or a lower compression ratio, the engineers, when they're trying to make an engine, they look at different things of how the car is going to be used, what kind of power they want or trying to get from the engine. So it's always, there are many variables, and a compression ratio, it's a big factor in that. So for example, if you make the compression ratio higher, the engine obviously could be more, you can create more power, and you can also make the engine more fuel efficient. And that's why in our example, the Elantra has the higher compression ratio. It's because it doesn't have any turbos, and they are trying to make it more fuel efficient. For those are one of the examples. And also why in the Genesis they decided to make it smaller, because the Genesis does have turbos, and they will be able to provide enough power, but it's still better to be safe than sorry, you know, because if they would have made a much higher compression ratio here, it could have been, detonation could have been a higher possibility with this engine. Also, if you have a low compression ratio, you can advance the timing for the ignition more without actually causing the detonation, and by doing so you're actually improving or increasing the high-end torque. By high-end I mean at the higher RPM ranges, so when the car is already moving fast. Low-end torque is from the start, and the high-end torque is when the engine is at the high RPMs. Yeah, so let's take a look under the hood, just to see the engine, because we haven't seen the 3.3 engine in the channel yet. Let's do that and continue from there. And there we go. It's placed a bit differently than the Elantra engine. We're actually going to get into the different configurations of engines, like the V or inline, and different number of cylinders that they can have and how they can be placed in the car in the next video. So stay tuned for that. And yeah, so right now I just wanted to show the 3.3 liter engine that we were calculating the displacement and the looking at the compression ratio. That's it for this video. Thank you very much for watching. Hope you enjoyed it. Like, subscribe like always, and see you in the next video. This was Driving Approach, Mechanics Corner. Bye.